I'm again back with the next lecture of spectroscopy. So this is the lecture 2, and we will be going through a short recap that we have learned in our previous lecture. So without any further delay, I will be going through it very quickly. Just keep yourself calm and just see this lecture and go through the notes, and you will be completely done and dusted. Okay, so on the previous lecture I have covered about principle of spectroscopy with the selection rule. So there we have learned about what is spectroscopy. Okay, the branch of science that studies the interaction of electromagnetic radiation with matter. Okay, there we have to know about the electromagnetic radiation behavior, dual nature behavior, and there we have learned the most important formula. Okay, how they are interconnected to each other and their symbolic expression. Then we have gone through what electromagnetic spectrum and spectroscopic region. Okay, there we have learned about this table, which is very important. Actually, overview of it is important. And then we have learned about the three primary photon matter events from the basic, that is our absorption, emission and scattering. You can go through the picture and diagram of it and you will get the idea completely. Then we have gone through what we have gone through resonance condition and the Bohr frequency rule, where we have said that a photon is absorbed only when its energy matches the gap between two molecular energy levels. That means del E is equals to E2 minus E1. Okay, that can be related with h nu, that can be also said as hc by lambda, or you can say that hc into nu bar. Okay, only photons with this exact nu are absorbed. Okay, off resonance photons pass through unchanged. This is why spectra shows discrete lines or bands instead of continuous. Okay. Then selection rule. Selection rule, we have got to learn about what selection rule is there. Here, when the resonance condition is satisfied, we go for the selection rule. For the selection rule, we actually see what comes from the requirement that the transition dipole moment integer will be non-zero. There we will say that P transforming from 1 to 2 is directly proportional to mu 1 to 2 whole square. Okay, that means what allowed transition is mu 1 to 2, that should be non-zero, strong band and high intensity, and forbidden transition is here for mu 1 to 2 is equal to 0 in the simple model band absent or very weak, you could say. So these are the whole thing. Generally there is the gross selection rule and specific selection rule. In the gross selection rule, we do what the molecule must possess property of like permanent or oscillating dipole capable of interacting with radiation. Okay, and then specific selection rule, the change is quantum numbers and must obey definite values. After all this, you could see these are the important things: selection rules across spectroscopy, rotational microwave, vibrational, Raman spectroscopy, electronics, that is our UV-Visible NMR and ESR. I think this is the most important part, so I'm giving start to it. Please don't miss out this complete table. I request go through it. And here I have already told you that why N2 shows no IR but Raman shows. The thing is very clear. N2 shows N2 is Raman active but not IR inactive. The thing is what that N2 is homonuclear, so its dipole moment is 0 throughout the spacing vibration. But in the Raman case, the vibration must change according to the polarizability of the electron cloud, and in the N triple bond N state there is a polarizability. That's why N2 is Raman active but IR inactive. I hope this part is also clear. Then after all this, now we have already learned about population of energy levels to Boltzmann distribution, and just remember this formula. This is very important formula. Okay, then we have gone through what resolution and line width, the Heisenberg limit as well. So the thing is very simple. If it is an excited state has a very short lifespan, then the line will be broader. If it have a long lifespan, the line will be sharper. That's a simple thing, and this is our mathematical expression. Go through the mathematical expressions; they are very very important, and even there are different surrounding causes due to which this broadening of line also takes place. So this is the fast overview of it. So this 5 minutes, and who have already learned can skip this 5 minutes. Now I'll be moving to today's topic. So today I will be trying to cover complete electronic spectroscopy, that is our also known as UV visible spectroscopy. Okay. First, let's get our bearings. What exactly do you know about UV visible spectroscopy, and what do you think that why UV visible spectroscopy is measured? So simply, I could say that it measures the absorption of ultraviolet light, okay, which spans from 200 to 400 nanometer, okay, and visible is from 400 to 800 nanometer. The energy is sufficient to promote a valence electron from filled orbital to empty high energy orbital. Due to this, what happens? Due to this, the resulting spectrum gives information about chromophores, conjugations, and concentration. What can we finally derive from it? Okay, due to this, because it moves electrons between electronic states, we call it electronic spectroscopy. Okay, by looking at what wavelength a compound absorbs, we can pull out critical information about it. So what are those critical information? I have already told you. Now coming to the part that types of electronic transition, that is the most important part, you could say. See, we have the actually, you know what, in electronic transition, and there is in basically organic molecule, there is bonding, yes, bonding, non-bonding, anti-bonding transition. Okay, in case of bonding, there is a sigma with pi bond, and in non-bonding there is lone pair. Okay, and in anti-bonding there is your sigma star and pi star. The four common electronic transition in increasing wavelength are listed below. So what is it? See, this part is very important, so I will request you to see this lecture, means like at least if you are not clear with what is happening, go through it one. See, first one is our sigma star bonding. Wait, yes, sigma star, the saturated alkane transition. You could see here the saturated alkane transition. The thus you could say that this takes massive amount of energy because sigma bonds are exceptionally strong. The sigma bonds are exceptionally strong. This needs high energy. Okay, so it occurs in simple saturated alkenes like methane or ethane. The energy gap is so large that it absorbs below 150 nanometer. This is called vacuum UV region because air absorbs light there. See, I am not saying this vacuum UV region, okay, because air absorbs light over here. I am writing it. Oops. Light over here. In this region, okay, so it occurs in simple saturated alkane. I have already told you about that. Okay, so particularly speaking, it is inaccessible, or you can say that in standard laboratory we cannot access this very easily in our spectrophotometers. So this is very typical one, you could say that. After this we have what we have, n sigma star. So what is n sigma star? That is our heteroatom transition seen in saturated compounds with lone pairs like your or water, CH3OH, alkyl halides, and amines. Okay, where you could see that it takes higher energy and absorb between in 150 to 250 nanometer. Fine. Then we have pi to pi star. Pi to pi star is actually the conjugation transition. I guess you have learnt about it already several times. I have told you about this is our heteroatom transition. I'm writing if it's not clear. This is our heteroatom. Okay, this is our heteroatom transition. and this is our conjugation. This is our conjugation. So in this conjugation transition found in alkane, alkynes, aromatics and carbonates, it requires medium energy and falls in 170 to 250 nanometer range, and then you can say that it actually absorbs between 150 to means like it actually seen in 170 to 250 nanometer, and it absorbed is 10 to the power 3 to 10 to the power 4. Okay, then this is the intensity. Then you can say that after this we have into pi star. Then into pi star is our what? Alkyl into pi star bonding means our lowest energy transition. This is the lowest energy transition. Lowest energy transition. Where we can find it in aldehyde, ketones. Okay. We generally found it, and there you can see that this happens in molecules containing heteroatoms with lone pairs attached to unsaturated system, like the carbonyl group in aldehyde. Okay, C double bond O group. And see, even you could see that because the energy gap is teeny, it absorbs at relatively longer wavelength, means like around 270 to 300 nanometer. And after this, however, its intensity is quite low because it is formally just a symmetry forbidden thing. Okay, so you have covered the most important part. Remember these transitions, they are important according to your exam point of view. Now I think one of the repeated question is your or Beard's Lambert's law. You could see this question very easily in your paper, either in 1 marks, either in 5 marks, or it could come as part of group C as well. So in UV visible spectroscopy, let me take this. After this, I will say that why is UV visible spectroscopy so popular in industrial labs? Simply, I could say that the reason is this Beard's Lambert's law, because it can tell us exactly how much of chemical is in a solution using this Beard's Lambert's law. And what does this Beard's Lambert's law states you? It states you about the factor of absorbance. Okay, that is linearly related to concentration through the Beard's Lambert's law. So here this is the formula. Okay, I'm coming to the formula. Let me get through the statement first. The statement is, it states that absorbance is directly proportional to concentration and path length. Okay, what does it means? Let me come over here. This A is called as our absorbance. Okay, you could see that is completely dimensionless. That you could say is equals to log distance I naught by I. What is your I naught? I naught is your incident intensity and I is your transmitted intensity. Okay, and here you could see is equals to epsilon CL. What is this epsilon? Epsilon is your molar absorptivity. Okay, and C is your concentration and L is your length. And please guys, this is too much important. Please remember the units. I don't know how much star I should give. Please remember the units. Beard-Lambert law is somewhat a game of units and everything. So clearly I would say that try to remember the units. I have mentioned it over here. Fine. After completing this, I will go through the limitations of Beard-Lambert law. Whatever comes in our life, everything has a limitation. So can we just use this formula for any solution? Actually, the thing is no. The law fails under certain condition. What are those conditions? See, this if this ideal conditions will not be there, this law will definitely fail. Firstly, the condition was high concentration. If the concentration is greater than 10 to the power minus 2 m, solute molecules interact. Okay, and epsilon is no longer constant. Fine. Then polychromatic light. Different wavelengths have different epsilon. Average becomes non-linear. Then stray radiation. Light reaching detector by leakage flattens absorbance at high A. Chemical equilibrium. In case of chemical equilibria, it if a dye dimerizes, ionizes or fluoresces, the effective concentration actually gets changed. So this is what chemical equilibria tells you. And I have already discussed about polychromatic light, that the law expects a single wavelength, and if the light source has multiple wavelengths, the relationship flattens out there. I hope every point is clear over here about the Beers-Lambert's law. I told you that according to exam point of view, the numerical is also important. That's why I have given here one numerical. See there, what are the data you could find here? A solution of organic dye gives absorption equals to 0.92 in a 1.0 centimeter cell at 510 nanometer or 10 nanometer, where epsilon is 2300 liter per mole centimeter inverse. So what are the data we are having already? We are having A is equals to 0.92. Fine. We are having, wait, let me take this pen. A is equals to 0.92. Fine. Then we are having what? Length. L is equals to what? 1.0 centimeter. Then what are we having extra? See, you don't need this frequency. Why do you need this wavelength? Okay, this wavelength is actually given to you to confuse. This is the confusing data actually. Okay, and then what you need? Epsilon. Epsilon is our what? 2300 liter mole inverse centimeter inverse. Done. See, I am telling you that this is the formula. A is equals to epsilon CL. There you already have your A, you have your epsilon, you have your L. Just you need to find what? C, and here is your C. C is equals to A by epsilon into L. C, just put the values, get your answer. Simple. And never get confused with this data. This is a confusing data given. You don't need it. Fine. After this, come to one of the most valuable. See, this whatever I am covering today, I think spectroscopy is one of the most important part I am covering in this complete lecture. So I guess within a half an hour you will be mastering almost the main parts of the spectroscopy. So now chromophores and auxochromes. So let's the vocabulary scientists use to describe this molecular absorption parts. So chromophore, this is directly responsible for absorbing. You know that what are the unsaturated functional groups? These are C double bond C, C double bond O, or you can say N double bond N or NO2. These are the things. Then you can say that what are auxochromes? Auxochromes are really some great kick things. This group does not absorb light on its own. Okay, they are like, I am not interested, bro. But when this auxochrome gets its partner, then it starts acting like, okay, I'm enthusiastic now. I will study. Now I will make you study. This is the factor how auxochrome behave. So basically you can say that this group does not absorb light on its own, but when attached to chromophore, auxochrome gets attached to chromophore, then what happens? It acts like an amplifier. Okay, I'm writing this word. I love this word using for auxochrome, amplifier. Okay, it acts as amplifier. These are the saturated groups containing lone pairs. Okay, you could see that non-bonding electron is present over here, lone pairs. When attached to chromophores, what happens is these lone pairs are pushed into the chromophores, and then they push this their lone pair into the chromophore, shifting the absorption to longer wavelength and increasing its peak intensity. Are you understanding that what the scenario is taking place? This auxochrome people has some lone pair. They do what? They give it to the chromophores, so that whatever chromophore is doing, they can continue doing it, and lambda max should be longer wavelength and hence increasing the intensity. See, Now we are coming to what? Now spectral shift terminologies. I'm telling you, these terminologies are way too important for your exam, and I'm telling one question, that is your barthochromic shift and hypsochromic shift. You need to learn the difference. I haven't added it over here. I will be adding difference. This is very important. I'm writing it for on behalf of you. Difference between these two. Prepare a set of difference. Important. From exam point of view, I'm just barthochromic shift is also known as red shift, and hypsochromic shift is known as blue shift, and hyperchromic shift, hyperchromic effect is there and hypochromic effect is there. Okay, so in barthochromic shift, lambda max increases to longer wavelength, and that means lower energy caused by high caused by extended conjugation or addition of auxochrome. Okay, this is the cause you can know. And in hypsochromic, or you can say in blue shift, if what happens, lambda max decreases to shorter wavelength, and that means higher energy happens when conjugation is completely disrupted. Then we are having what? Hyperchromic effect. The intensity, that is epsilon, of the peak increases, and in hypochromic effect the intensity of epsilon of the peak decreases. Fine. Why these are happening? Because of this symmetry, it will increase in case of hyperchromic, and hypochromic distortion of chromophore is there. Effect of conjugation. Now see, the power of conjugation comes over here. There is a beautiful rule. Okay, more conjugation is equals to longer wavelength. Simple thing, in one way you can say this. I am writing it for you so that you can remember. These are the small things that makes your day, and you simply will remember in your exam hall. Oh, these are the things, this was the thing. I am writing it. More conjugation, longer wavelength. Fine. So why every time you add a conjugation C double bond C in the molecular orbital system, do you think expands? See, the thing is very simple. This raises the energy of highest occupied molecular orbital, that is our HOMO. Wait, let me fix it. Mark it. Your HOMO and LUMO. Okay, the story comes over here that this raises the energy of HOMO and lowers the energy of LUMO. As a result, this HOMO-LUMO gap shrinks. So lambda max moves to longer wavelength. That means you need what? Lesser energy required for transition, meaning it absorbs longer wavelength. This is the whole factor of conjugation. See, here I have mentioned some compounds such as ethylene, 1,3-butadiene, 1,3,5-hexatriene, beta-carotene as well. So go through them. I could say only one thing about this beta-carotene is that in this beta-carotene 11 conjugated double bonds are present. That means shifts all the way out to 470 nanometer. Can you imagine? Because it absorbs the blue violet visible light, it reflects a bright orange color. Exactly, this is the reason why your carrot, due to the presence of this beta carotene, means like looks orange, because it absorbs blue violet visible light but reflects black the bright orange color. Fine. After this, now coming to your solvent effect on electronic spectra. What is this? You will see this. What is wrong with this? I have already learned. Can the solvent affect our spectrum? Actually, yes. Polar protic solvent stabilizes ground states and excited states differently. So what is it? For a pi to pi star transition, there is barthochromic redshift. I told you, you will be making a, see, I am uploading this lecture on 10th, so I expect you will be seeing it on 10th. Try to prepare a proper difference and send it to me through my WhatsApp. into the wingman, and I will be definitely getting back to you guys, and comments your doubts, man. I will be taking a live session for doubt clearing after completing the lectures. So orthochromic shift is there, and then excited state is pi star, that is more polar and better stabilized. Okay, and in hypsochromic shift, that is your blue shift, that is happening in N to pi star transition. The polar solvent from the stronger hydrogen bonds with the ground states lone pair, this drops the ground state energy significantly, widening the energy gap and cause a hypsochromic blue shift. Are you understanding what is happening? See, here is the main scenario is about your pi star, and here the main scenario is about the bonding of lone pair. Fine, please, I request go through the difference one. It's one of the most valuable question I could say you. Now what is there inside the instrument? Our instrument is what? Double beam spectrophotometer. Okay, let's look at the diagram. In modern lab, we have this double beam spectrophotometer. Instead of running your sample and blank solvent separately, a beam splitter is used, and then this beam goes through this sample cell and reference cell, means like separately, okay, simultaneously and separately in two parallel pathways. One goes through, means like, and then after this the detector subtracts the reference background in real time, eliminating any kind of error in it. Okay, finally you will be getting every requirements in this detector and amplifier, then it will be recorded, or you can say displayed. So this was the whole thing. Now what are the source of this light? This I told you about the light source, right? What are this light source? This light source are generally these three what I am mentioning over here. One is deuterium, tungsten, or you can say halogen lamp, or you can say xenon flash lamp. And where the region lies, you could see if it is deuterium, then it is UV region. If it is tungsten halogen, then it is in visible region. Xenon on flash, then it is UV visible. Okay, so finally let's just wrap up the session with the application of UV visible spectroscopy. There you could see that quantitative estimation of metal ions, determination of molar absorbability and concentration in pharmaceuticals, detection of conjugated system and aromatic rings, reaction kinetics, and then identification of dyes and impurity profiling. So this is the overall view of our electronic spectroscopy. To wrap up here, I think your high yield exam keys are already covered in it, and please go through Beer's Lambert's law, numericals, and difference between chromophore, auxochrome, and then barthochromic shift and hypsochromic shift, and just wait for the part, means like lecture 3, and there I will be covering your fluorescence part, and I hope you will be getting all the insight from it. So thank you.